Welcome to Earth Analyst. Have you ever wondered what would happen if you were in space and you ended up getting close to the black hole, and you got close to it? Well, in today's video, I will be going over what if you fell into a black hole. I also want to know where you're watching this video from and what time it is for you, because I am about to take you on a long space journey. In the vast, hushed auditorium of the universe, where galaxies swirl in elegant spirals across spans of billions of years, humanity sits as a fragile newcomer, an audience of one on a tiny, precarious stage. We peer outward into the infinite, a canvas painted with glowing nebulae, ancient beams of starlight, and an overwhelming sea of darkness. Yet the distances are merciless. They measure our isolation not in miles, but in epochs that make human lifetimes seem like fleeting sparks. With our fastest spacecraft, a voyage to Proxima Centauri, our closest stellar neighbor, would demand more than 50,000 years. The Andromeda Galaxy, though considered nearby on cosmic scales, shines with light that began its journey when our distant ancestors first set foot upon the Earth. Confronted with this unfathomable expanse, humanity has always longed for a hidden passage, a secret tunnel through reality itself. And in that longing, our eyes often settle upon the most mysterious and terrifying titans of the cosmos, black holes. These are nature's ultimate traps, regions where gravity becomes so extreme that not even light can break free. They are thresholds of no return, the final chapter in a star's existence. Yet an irresistible thought lingers. What if these cosmic prisons are not endings, but beginnings? What if black holes conceal not walls, but doorways, gateways to distant realms, to other eras, or perhaps even to universes beyond our own? This is the tale of the wormhole, a hypothetical bridge that tunnels through spacetime, intricately tied to the mysteries of black holes. It's a story that carries us to the frontier of physics, where the rules of reality bend, fracture, and unveil possibilities that defy imagination. The origin of this idea, the Einstein Bridge, begins not in the distant future, but in the early 1900s, with the man who reshaped our view of existence itself. In 1915, Albert Einstein revealed his general theory of relativity. He didn't merely adjust Newton's vision of gravity, he shattered it entirely. Gravity, Einstein declared, was no invisible tug at a distance. Instead, it was the natural result of the universe's geometry. He pictured a four-dimensional fabrics, time-woven from the three dimensions of space and the one of time. Massive objects, like stars and planets, did not pull on their neighbors. Rather, they bent and curved this fabric. Imagine a bowling ball resting on a taut rubber sheet. The ball sinks in, shaping a depression. A marble rolled nearby will spiral around it, the straightest possible line across the curved surface. This, Einstein revealed, is gravity. His field equations, mathematical blueprints of this idea, described how mass and energy sculpt spacetime's shape, and soon after he published them, physicists began to explore their solutions, chasing the strange possibilities hidden in the mathematics. In 1916, K.L. Schwarz found the first exact solution for a single, non-rotating spherical mass, a solution that described the spacetime around what we now call a black hole. It was a bizarre discovery, predicting a region with an event horizon, a one-way membrane, and at its center, a singularity a point of infinite density where the known laws of physics collapse. For years, this singularity was a mathematical headache. But in 1935, Einstein himself, working with fellow physicist Nathan Rosen, explored a peculiar aspect of the solution. They tried to remove the singularity mathematically by extending the solution. In doing so, they found something extraordinary. Their equations described not just one indentation in spacetime, but two connected by a sort of throat or bridge. It was as if the bottom of the funnel, created by the black hole, opened up into an identical inverted funnel. This structure, formerly known as the Einstein-Rosen bridge, was the first theoretical description of a wormhole. The mathematics suggested that a black hole wasn't just an endpoint. It was an entrance to a tunnel that emerged somewhere else in spacetime through an object. That was its exact opposite, a white hole, a hypothetical region from which matter and light could only escape, never enter. A black hole was the entrance. A white hole was the exit. On paper, it was a perfect, elegant gateway. The fatal flaw, a bridge of ghosts. The discovery of the Einstein-Rosen bridge was a stunning theoretical revelation. It hinted that the universe could possess a topology far more complex than we had ever imagined, with hidden tunnels crisscrossing the void. However, the dream of riding this cosmic subway was dashed almost as soon as it was conceived. When other physicists, like John Wheeler, who coined the terms black hole and wormhole, analyzed the dynamics of the bridge, they discovered a fatal flaw. The Einstein-Rosen bridge is catastrophically unstable. The throat connecting the black hole entrance to the white hole exit is not a static structure. According to the mathematics, it opens and closes with incredible speed. The time it takes for the throat to pinch off into a singularity is shorter than the time it would take for even a photon of light to travel from one side to the other. This means it is not untraversable. Any object or any astronaut brave enough to plunge past the event horizon of the black hole would not find a waiting tunnel to another galaxy. Instead, they would find the bridge collapsing in on them, sealing them off and crushing them at the inevitable singularity. The gateway would slam shut before they could even get through the door. Furthermore, the white hole itself is a purely hypothetical and problematic concept. While they are valid solutions to Einstein's equations, they are thought to be physically impossible to form in the real universe. Unlike black holes, which form naturally from the collapse of massive stars, there is no known process that could create a white hole. They would violate the second law of thermodynamics, as their decreasing entropy would be like watching a shattered egg spontaneously reassemble itself. So, not only was the bridge impossible, but its exit probably didn't even exist. The beautiful Einstein-Rosen bridge was a mathematical ghost, a fleeting possibility that could never be realized. The gateway, it seemed, was permanently locked, propping open the door, the enigma of exotic matter. For decades, the idea of a traversable wormhole remained in the realm of science fiction. Then, in the 1980s, physicists like Kip Thorne, a leading expert on general relativity, revisited the problem with a new question. Instead of asking if wormholes exist, they asked what would the laws of physics require for a traversable wormhole to exist. The answer they found was as strange as the concept itself. You would need to prop the throat open, and the material required to do that is something we have never seen, something that seems to defy common sense. They called it, to understand why, we must return to gravity. The immense gravity that forms a black hole also wants to crush a wormhole's throat. To counteract this, you need a material that generates anti-gravity. You need something that pushes space-time apart rather than pulling it together. This requires matter with a negative energy density, or equivalently negative pressure. Imagine holding a ball of this substance. It wouldn't just be weightless. It would have anti-weight. It would fall up. It would push back on your hand. It would weigh less than nothing. This is not to be confused with antimatter, which has positive mass and energy and behaves gravitationally just like ordinary matter. This is something else entirely. A substance that violates what physicists call the null energy condition. Placing a ring of this exotic matter at the throat of a wormhole could, in theory, generate enough repulsive gravitational force to hold it open, creating a stable, traversable tunnel through space-time. A spaceship could then, in principle, fly through without being crushed. The search for a shortcut through the cosmos had become a search for a substance that may not even exist. Is there any evidence for such a thing? The answer is a tentative, microscopic maybe. In the quantum world, the Casimir effect demonstrates that empty space is not truly empty. It's a rowing foam of virtual particles popping in and out of existence. If you place two parallel metal plates very close together in a vacuum, the pressure from the virtual particles outside the plates is greater than the pressure between them, pushing the plates together. The region between the plates can be said to have a negative energy density relative to the space around it. However, the effect is unimaginably small and localized. To stabilize a wormhole large enough for a person to pass through, you would need vast quantities of exotic matter, an amount comparable to the mass of a large planet with a negative density that is extreme and stable. We have absolutely no idea how to produce or contain such a substance. Even if we could somehow conjure up enough exotic matter, the journey through a wormhole would be fraught with perils. Entering the wormhole could become trapped, bouncing back and forth between the mouths and amplifying in energy with each pass. This feedback loop would be exponentially powerful, creating an intense storm of high-energy radiation that would instantly incinerate any traveler. This blue shift effect would effectively create a firewall of energy, destroying the wood traveler and likely the wormhole itself. But perhaps the most profound and disturbing consequence of a traversable wormhole is that it is inherently a time machine. This isn't a speculative add-on. It falls directly out of Einstein's own theories. According to special relativity, time passes more slowly for an object that is moving at high speed, an effect called time dilation. Now imagine you have a stable wormhole with both mouths, sitting stationary in your laboratory in the year 2050. You take one mouth, attach it to a spaceship, and send it on a round trip at nearly the speed of light. When it returns to the lab, only 1 year might have passed for the moving mouth, while 10 years have passed for the stationary one. The stationary mouth is now in the year 2060, but the mouth that went on the trip is in the year 201. You can now walk through the stationary mouth in 60 and emerge from the other mouth in 201. You have just traveled 9 years into the past. This opens the door to all sorts of logical nightmares. Chief among them, the grandfather paradox. What if you travel to the past and accidentally prevent your own birth? How can you exist to have made the journey in the first place? Physicists have proposed two main ways out of this conundrum. The first is the Novikov self-consistency principle, which essentially states that the laws of physics forbid paradoxes. You can travel to the past, but you are not free to change it. Your actions would be part of a self-consistent causal loop. You would find that no matter what you tried, your actions would only help to create the very past from which you came. Free will in this scenario would be an illusion. The second idea is the many worlds interpretation of quantum mechanics. In this view, traveling to the past shunts you into a parallel universe. You can change the past in that timeline, creating a new branch of history. But your own original timeline remains untouched, the verdict, a dream deferred. So, could a black hole be a gateway? The answer, according to our best current science, is almost certainly no. The simple natural black holes formed from collapsed stars are the non-traversable, crushed to a singularity kind described by the original Einstein-Rosen bridge. The creation of a traversable wormhole, a stable gateway, would require feats of engineering so far beyond our capabilities that they might be impossible in principle. It would demand the existence of vast quantities of exotic matter, a substance we've never observed and don't know how to create. It would require us to solve the immense problems of radiation feedback and tidal forces, and it would force us to confront the universe-altering paradoxes of time travel. While we haven't found any evidence of natural wormholes through methods like looking for their unique gravitational lensing effects, the idea remains a powerful driver for theoretical physics. It forces us to ask the deepest questions. What are the ultimate limits of manipulating space-time? Is causality a fundamental law, or can it be violated? Are there other universes? The black hole in this sense remains a gateway after all. Not physical gateway to another star system, but a theoretical gateway to a deeper understanding of the cosmos. It is a portal in our minds that leads to the furthest frontiers of knowledge, reminding us that the universe is not only stranger than we imagine, but stranger than we can imagine. The shortcut remains a dream, but it is a dream that illuminates the magnificent complexity of the reality we inhabit. White holes, the opposite of black holes. In the grand lexicon of the cosmos, few words carry the weight of finality like black hole. It is the ultimate abyss, a one-way journey into oblivion. We have explored its nature as a cosmic prison and even toyed with the romantic notion of it as a gateway. But in the elegant, often symmetrical world of theoretical physics, an irresistible question arises. If the universe permits an object that only swallows, does it also permit an object that only spews? If there is an ultimate sink, must there also be an ultimate fountain? This is the story of the cosmic antithesis, the perfect mirror image of a black hole. An object so fleeting and paradoxical that it may only exist on the chalkboards of theorists and in the deepest recesses of our imagination. This is the story of the white hole. To contemplate a white hole is to gaze into a cosmic looking glass. It is to take everything we understand about a black hole, its inescapable gravity, its dark finality, its inexorable pull, and turn it completely on its head. It is a place where matter and light can only leave, never enter, a point of origin, not a destination, a constant violent eruption from a singularity rather than a silent eternal collapse. They are the phantoms born from the same equations as their dark twins. a testament to the fact that in mathematics time can run both forwards and backwards. But the crucial question remains: does the universe itself allow for such a rewind button? Born from the same ink, the mathematical twin, the concept of a white hole did not emerge from an astronomer's observation or a wild new theory. It emerged, like the black hole itself, from the dense and beautiful mathematics of Albert Einstein's general theory of relativity. When Karl Schwarz first solved Einstein's equations for a non-rotating mass, he provided a geometric map of the spacetime around it. This map, however, wasn't complete. Physicists who later studied the solution, like John Wheeler and Martin Kreskel, sought to create a maximal extension of the Schwarzschild geometry. This is a mathematical exercise to map out every single possible path that a particle or a photon could take in this particular spacetime, without running into an artificial edge. When they did this, the resulting diagram, known as a crucial secret diagram, revealed a shocking level of complexity. It contained not just our familiar universe and the interior of the black hole, but to other regions as well. A parallel universe, or another separate region of our own universe, and its inverse twin, the white hole. The complete mathematical solution described a structure connecting all four of these regions via an Einstein-Rosen bridge. The key to understanding this is the nature of the singularity. For a black hole, the singularity is a point of infinite density that lies in the future. Every path that crosses the event horizon inevitably ends at the singularity. It is a future destination from which there is no escape. The mathematics, however, is time symmetric. You can just as easily write down a solution where the singularity lies in the past. This is the white hole. It is a past origin from which everything must emerge. Think of it like a film reel. A black hole is the film played forward. A star collapses, an event horizon forms, and matter disappears into a singularity. A white hole is that exact same film played in reverse. A singularity erupts, an anti-event horizon forms, and matter and light pour out into the universe. It is a perfect time reversal of a black hole's formation and existence. On paper, it is every bit as valid a solution as the black hole. But physics is more than just equations. It must also bow to the harsh realities of the physical world. If we could hypothetically observe a white hole, what would its properties be? It would be a spectacle of cosmic violence and defiance. At its boundary lies the anti-event horizon. Like a black hole's horizon, it is a point of no return, but in the opposite direction. For a black hole, once you're in, you can never get out. For a white hole, if you're out, you can never get in. Any particle or photon from the outside universe directed at a white hole would travel towards it, but time would stretch infinitely as it approached the horizon. It would never actually reach it in a finite amount of time. The light heading towards it would be catastrophically blue-shifted, its frequency and energy increasing towards infinity, effectively creating an impenetrable wall of energy at the horizon. The singularity of a white hole, as we've seen, is a past singularity. It is not a place you can go to. It is the place where everything spewing from the white hole came from. It is the source, the genesis point of all the matter and energy that erupts from the white hole's mouth. This constant eruption would make a white hole an intensely luminous object. It would not be black. It would be blindingly white, a beacon. of ceaseless creation, pouring new information and material into the universe. The light leaving it, fighting against its immense gravitational pull, would be severely redshifted, its wavelength stretched, and its energy lowered, but it would still be a source of constant radiant output. In essence, it would be the universe's most powerful firework, a firework that never ever stops. Here we arrive at the great wall that separates the mathematical possibility of a white hole from its physical reality, the second law of thermodynamics. This is not just a suggestion. It is one of the most robust and fundamental pillars of all physics. It states that in any closed system, the total amount of entropy, a measure of disorder, randomness, or waste heat, will always increase over time. This law is woven into the very fabric of our experience. A hot cup of coffee cools down, dispersing its heat into the room. It never spontaneously gathers heat from the room to become hotter. An egg can scramble, but it cannot unscramble. A building crumbles into dust. Over centuries, dust does not spontaneously assemble itself into a building. The universe has a clear arrow of time pointing from order to disorder. Black holes are paragons of this law. When a highly ordered star collapses into a black hole, it might seem like information and order are lost. But Jacob Binstein and Stephen Hawking showed that a black hole has an enormous entropy proportional to the surface area of its event horizon. As matter falls in, the black hole's mass and horizon area increase, and thus its entropy increases. The universe becomes more disordered, and the second law is upheld. A white hole commits the ultimate thermodynamic crime. It is a system of spontaneously decreasing entropy. It begins with a singularity, a single point of maximum order, and explodes outward, creating complex structures like atoms, dust, and radiation. This is like watching the scrambled egg perfectly separate back into its yolk and white. It is a process that runs contrary to the universe's fundamental arrow of time. For a large macroscopic object like a white hole to exist, it would mean that one of the most foundational laws of physics is at best optional. This is a claim so extraordinary that most physicists reject it outright. The universe, it seems, does not like to run its processes in reverse. Even if we were to ignore the thermodynamic problem, the white hole faces another fatal flaw: extreme instability. It could only exist in a universe that is perfectly pristine and empty. The moment a single photon of light or a single hydrogen atom from the outside universe were to head towards a white hole's event horizon, its fate would be sealed. As that piece of matter gets closer to the horizon, the intense gravitational field causes its energy to skyrocket from the perspective of an observer falling out of the white hole. This infinitely blue-shifted energy would effectively add to the white hole's mass. The slightest perturbation from the outside world is enough to shatter the fragile time-reversed solution. The naked past singularity of the white hole is so abhorrent to the universe that it would instantly cloak itself in the respectable stability of a black hole's event horizon. A white hole is like a perfectly balanced needle. Standing on its tip, the slightest breeze will cause it to topple over into a much more stable state. Our universe is filled with such breezes. The cosmic microwave, background radiation, stray particles, and light from distant galaxies. In a real dynamic cosmos, a white hole wouldn't stand a chance. Given these seemingly insurmountable obstacles, is the white hole story over? Not quite. Some theorists working at the speculative edge of physics have tried to find scenarios where white hole-like phenomena might appear in a physically plausible way. One of the most compelling ideas comes from the ultimate fate of black holes. According to Hawking radiation, black holes are not entirely black. They slowly leak radiation and evaporate over immense timescales. For a solar mass black hole, this process takes longer than the current age of the universe. But what happens at the very end, when the black hole has shrunk to a microscopic quantum scale, the Planck scale? The laws of general relativity break down and quantum gravity must take over. Some physicists like Carlo Relli and Hal Hagd have proposed a black hole bounce. They suggest that the immense gravitational pressure inside the black hole could be counteracted by a quantum repulsive force, preventing the formation of a true singularity. Instead, the collapsing matter would reach a point of maximum density and then bounce, re-emerging in a violent, explosive event. The end of a black hole's life could be its rebirth as a short-lived, microscopic white hole. This theory cleverly links the two opposites and avoids the thermodynamic problems because it's a quantum phenomenon that occurs over vast timescales, preserving the overall arrow of time. Another tantalizing, though highly speculative idea, is that our own Big Bang was a type of white hole. It was, after all, a past singularity from which all the ordered matter and energy of our universe emerged, and our expanding cosmos has been increasing in entropy ever since. Under this model, our entire observable universe could be the interior of a gargantuan white hole. While this is a fascinating picture, it's more of a cosmological analogy than a testable theory, and simply pushes the question of origins one step further back. What then is outside the white hole? The white hole remains one of the most beautiful and frustrating concepts in modern physics. It is the perfect twin, the logical opposite, born from the very same mathematics as its famous sibling, and yet it appears to be a ghost in the machine of reality. Its existence would require the universe to rewind time and violate its most sacred law of thermodynamics. Its structure is so fragile that the slightest touch from the outside world would cause it to vanish, reborn as the very thing it was meant to oppose. While astronomers actively hunt for black holes, no one is seriously searching for a white hole. They are not expected to exist, but their story is not one of failure. The study of white holes forces us to appreciate the profound asymmetry of our universe. Time, it seems, truly is a one-way street. Entropy provides a powerful and unwavering arrow, guiding the cosmos from the order of the past to the chaos of the future. The white hole serves as a crucial thought experiment, a theoretical foil that by its very implausibility illuminates the deep physical principles that make our universe stable, predictable, and relentlessly forward-moving. It is the phantom that haunts Einstein's equations, forever reminding us that just because you can write something down, it doesn't mean the universe has to build it. Picture a galaxy, perhaps our own Milky Way, a breathtaking, pinwheeling metropolis of 400 billion stars intertwined with luminous clouds of gas and dust, spanning 100,000 light-years from edge to edge. It is a structure of almost incomprehensible scale and majesty, a cosmic city humming with the birth and death of suns. For centuries, we saw this as a beautiful, almost random collection of stars held together by their mutual gravity. But we have since discovered that this is not the full picture. We have learned that at the very heart of this stellar city, shrouded in gas and hidden from our eyes, lies a monarch, a gravitational tyrant of unimaginable power and proportion, a monster that governs the motions of the entire galactic core. This is not just any black hole. This is a supermassive black hole. These are not the ghosts of single dead stars. They are a class of object entirely unto themselves. Behemoths that weigh as much as millions or even billions of our suns. They are the beating hearts of nearly every large galaxy, including our own. They are not merely passive anchors sitting silently in the dark. They are cosmic engines that can outshine their entire host galaxy. They are galactic architects that regulate the birth of stars and shape the very evolution of the cosmic structures they inhabit. To understand a galaxy we have found, we must first understand the monster that lurks in its heart. This is the story of the universe's ultimate heavyweights, the silent rulers of the night. Before we venture into the galactic core, it's crucial to understand the sheer sense of scale that separates these giants from their more common cousins. The universe is littered with stellar mass black holes. These are the endpoints of very massive stars, perhaps 20 times more massive than our sun. When such a star exhausts its nuclear fuel, its core collapses under its own immense gravity, forming a black hole with a mass typically between 3 and 100 times that of our sun. They are the normal black holes, the predictable ghosts of stellar evolution. A supermassive black hole, SMBH, is something else entirely. They are not measured in tens or hundreds of solar masses, but in millions and billions. To put this in perspective, let's consider our own galaxy's central resident, an SMBH named Sagittarius. It weighs in at a staggering 4.3 million solar masses. If our sun were a single grain of sand, a typical stellar mass black hole would be a handful of sand. Sagittarius A** would be a sphere of sand weighing over 4 tons. The supermassive black hole at the center of the galaxy, Messier 87, M87, the first one ever to be directly imaged, tips the scales at an astonishing 6.5 billion solar masses. That's a mass greater than our entire solar system, from the sun out to the furthest dwarf planets, all compressed into a region of space. The most mind-bending aspect of these objects is their density. Despite its 4.3 million solar mass heft, the event horizon of SG*, its point of no return, is only about 24 million kilometers across. This means the entire object would fit comfortably inside the orbit of Mercury. It is a concentration of mass and a warping of spacetime so extreme that it belongs to a category of physics all its own. For decades, the existence of SMBHS was purely theoretical. We saw strange and violent phenomena at the centers of galaxies, but we had no smoking gun. That all changed in the late 1990s and early 2000s thanks to the painstaking work of 2 independent teams of astronomers, led by Reinhard Genzel and Andrea Gezi, a feat for which they shared the 2020 Nobel Prize in Physics. Their target was the heart of the Milky Way, a region so obscured by dense clouds of interstellar dust that it's impossible to see in visible light. Using powerful infrared telescopes that could pierce through the veil, they did something brilliantly simple in concept, yet incredibly difficult in practice. They watched the stars. For over 2 decades, they meticulously tracked the movements of individual stars orbiting the galactic center. What they found was stunning. Stars were whipping around a central unseen point at incredible speeds. One star named S completes a full orbit in just 16 years, reaching speeds of over 25 million km/h as it makes its closest approach. By applying Kepler's laws of planetary motion, the same laws that describe how planets orbit our sun, they could use the speed and size of these stellar orbits to calculate the mass of the object they were all circling. The calculation was unambiguous. There had to be an object with the mass of over 4 million suns packed into a tiny region at the center of these orbits. An object so massive and so compact could be nothing else. A dense cluster of stars would have either collapsed or been ripped apart. A cloud of gas would not be dense enough. The only known object that fit the evidence was a supermassive black hole. We couldn't see it, but we could see its absolute gravitational dominion over everything around it. The monster had been found. This discovery was followed by the ultimate confirmation. In 2019, the Event Horizon Telescope (EHT) collaboration, a global network of radio telescopes synchronized to create a virtual Earth-sized observatory, achieved what was once thought impossible. They captured a direct image of a black hole's shadow. Their target was the colossal SMBH in the galaxy M87. The image is now iconic, a dark central region. The shadow cast by the event horizon, surrounded by a lopsided glowing ring of superheated gas and plasma swirling into oblivion. This was the first time humanity had ever laid eyes on the abyss itself. In 2022, they succeeded again, capturing the image of our own. The evidence was now undeniable. Confirming the existence of SMBHs solved one great mystery, but opened another, even more profound one. How do they get so big so fast? We understand how a 10 solar mass black hole forms, but how does the universe build one that weighs billions of suns? This is one of the most active areas of research in astrophysics today, and several competing theories are on the table. The process must begin with a seed. One possibility is that the seeds were the black hole remnants of the universe's very first stars, known as population 3 stars. These pristine stars, formed from only the hydrogen and helium of the Big Bang, were true giants, hundreds of times the mass of our sun. When they died, they could have left behind black holes of a few hundred solar masses, providing a solid starting point. Another, more exotic idea is that of primordial black holes, seeds formed not from stars at all, but from the direct collapse of overdense regions of matter in the fury of the Big Bang itself. But a seed of a few hundred solar masses is a long way from a billion. How does it grow? One method is through steady accretion, where the black hole acts like a cosmic vacuum cleaner, slowly pulling in and consuming gas, dust, and any unlucky stars that venture too close. However, there's a physical limit to how fast a black hole can feed, and many calculations suggest this process is too slow to explain the enormous quasars, blazingly bright galactic centers powered by feeding SMBHs that we see in the very early universe less than 1 billion years after the Big Bang. This has led to more dramatic models. A leading theory is runaway merges. The early universe was a chaotic place with small proto-galaxies constantly crashing into and merging with one another. When two galaxies merge, their central black holes will eventually sink to the center of the new larger galaxy, orbit each other, and finally merge in a cataclysmic event that sends out powerful gravitational waves. Repeat this process over billions of years, and you can build a true giant. Perhaps the most radical idea is direct collapse. In the dense, turbulent environment of the early cosmos, some truly vast clouds of primordial gas weighing as much as 100,000 suns might have been able to do something extraordinary: collapse directly into a massive black hole, bypassing the star formation phase entirely. This would give the SMBHs a tremendous head start, creating a massive seed almost overnight. The James Webb Space Telescope, with its ability to peer back to the cosmic dawn, was designed precisely to find the light from these first galaxies and help us solve this ultimate chicken and egg problem. Perhaps the most revolutionary discovery about SMBHs is that they are not just quiet tenants in their galactic homes. They are active participants, architects that shape and regulate the evolution of their entire galaxy in a stunning feedback loop. This idea is supported by a remarkable observation known as the M-sigma relation. Astronomers found a tight, undeniable correlation between the mass of a galaxy's central black hole M and the average speed of the stars in its central bulge sigma. This is a profound discovery. It's like finding that the mass of a volcano on Earth is perfectly correlated with the speed of continental drift. Why should the mass of an object that is 1,000,000 times smaller than its galaxy be so intimately linked to the properties of the whole galaxy? It implies that the black hole and the galaxy did not form independently. They must have coevolved. They grew up together, influencing each other's development. The mechanism for this coevolution is called galactic feedback. When an SMBH is actively feeding during its bright quasar phase, it is an incredibly messy eater. As matter swirls into its accretion disk, friction and magnetic fields heat it to millions of degrees, causing it to radiate a colossal amount of energy. Furthermore, powerful magnetic fields can funnel some of this material into two spectacular jets of particles, which are blasted out of the galactic core in opposite directions at nearly the speed of light. How do you search for an object that is ancient, invisible, and could be anywhere? The hunt for PBHs is one of the most ingenious efforts in modern astronomy, relying on looking for the subtle, indirect effects these phantoms might have on the cosmos. The most famous search method relies on the work of Stephen Hawking himself. His theory of Hawking radiation predicts that all black holes slowly evaporate by emitting particles. The rate of this evaporation is inversely proportional to the black hole's mass. The smaller it is, the faster it evaporates. A PBH with the mass of our Sun would take an unfathomably long time to evaporate, but a PBH with the mass of a mountain, about 10⁻⁴ kilogram, would have been evaporating for the entire age of the universe, and should be reaching the end of its life right now. This death would not be silent. It would end in a final, brilliant burst of high-energy gamma rays. Gamma-ray telescopes have scanned the skies for these unique death flashes, but have found none. This allows us to rule out the existence of PBH within a specific low-mass range. For larger PBHs, astronomers use gravity itself as a lens. According to Einstein, the gravity of a massive object can bend and magnify the light from a more distant object behind it. This is called gravitational microlensing. If a PBH in our galaxy's halo were to pass directly in front of a star in a nearby galaxy like Andromeda, its gravity would briefly magnify the star's light, causing it to brighten for a short period. Extensive surveys have monitored millions of stars looking for these telltale brightening events. While they have found some, the number of events is far too low to account for a large population of PBHs, placing tight constraints on them in the mass range from a fraction of Earth's mass up to a few hundred solar masses. The ultimate prize, a solution to everything, given the lack of evidence. Why do physicists remain so captivated by the idea of primordial black holes? The reason is simple. Their existence would be a silver bullet, potentially solving two of the greatest and most persistent mysteries in all of science in one fell swoop. The first is the puzzle of dark matter. For decades, we have known that the universe is filled with an invisible substance whose gravity holds galaxies together and governs their rotation. This dark matter makes up about 85% of all matter in the cosmos. Yet, we have no idea what it is. The leading candidates are undiscovered subatomic particles. But what if dark matter isn't a new particle at all? What if it's just a vast population of ancient PBHs forged in the Big Bang? They are massive, they don't interact with light, and they would be distributed throughout the galactic halo, exactly where dark matter needs to be. While many mass ranges for PBHs have been ruled out as the dominant source of dark matter, a window remains open, particularly for those with the mass of asteroids. The second is the seeding of supermassive black holes. As we've seen, it's difficult to explain how SMBHs grew to billions of solar masses so quickly in the early universe. The direct collapse of primordial gas clouds or the slow merger of stellar mass black holes face significant challenges. But if a population of heavy PBHs formed in the Big Bang with ready-made masses of thousands or tens of thousands of suns, the problem vanishes. These PBHs would provide the perfect gravitational seeds, which could then grow rapidly by accreting gas and merging icily, forming the quasars we see at the cosmic dawn. Conclusion: a tale of two destinies. The contrast between these two types of black holes could not be more stark. The stellar mass black hole is a known quantity, a creature of established physics, born from the observed life cycles of stars. Its existence is written in the light of supernovae, the orbits of companion stars, and the gravitational waves that ripple across the cosmos. It is the end of a story. The primordial black hole, by contrast, is the beginning of a story that may not even be true. It is a phantom from the universe's first breath, an elegant and powerful hypothesis that remains tantalizingly beyond our grasp. The search for it is a search for the universe's oldest relics, a quest driven by the immense explanatory power it would hold. Finding just one would be a discovery of monumental importance, rewriting our understanding of cosmology. This tale of two black holes perfectly encapsulates the scientific endeavor. It is a story of the known and the unknown, of confirmed facts and brilliant speculation. One is the solved case. The other is the cold case that continues to baffle and inspire the world's greatest detectives, who continue to scan the skies for the slightest clue, hoping one day to prove that the ghost is real. An accretion disk is a structure formed by diffused material in orbital motion around a massive central body. This is the first step in the journey of matter toward a black hole. Picture a cosmic whirlpool, an immense flattened spiral of gas, dust, and plasma swirling with incredible speed and ferocity. This is the accretion disk, a structure of immense power and beauty, and the final feeding ground for a black hole. The matter that forms an accretion disk comes from many sources. It could be the remnants of a star that strayed too close to the black hole's gravitational pull and was torn apart. It could be the vast clouds of interstellar gas and dust that a black hole is traversing. Or it could be matter siphoned from a binary companion star in a cosmic dance of destruction. Regardless of its origin, this matter doesn't fall straight into the black hole. It possesses angular momentum, a rotational energy that causes it to orbit the black hole rather than plunging directly in. This is the same principle that keeps Earth from falling into the sun. However, in the case of a black hole, this angular momentum is immense, and the gravitational forces are mind-bogglingly strong. As the matter orbits the black hole, it can't maintain a perfect, stable orbit forever. Friction and viscosity, the stickiness of the gas and dust, cause the material to lose energy. This loss of energy allows the matter to spiral inward, gradually getting closer to the black hole. The particles in the disk are constantly colliding with one another, converting their kinetic energy into heat. This process is so efficient that the accretion disk becomes one of the brightest and most energetic phenomena in the universe. It can outshine an entire galaxy of stars, making black holes, which are by their very nature invisible, detectable across vast cosmic distances. The temperature of the disk can reach millions or even billions of degrees, hot enough to emit radiation. Across the electromagnetic spectrum, from radio waves to X-rays and gamma rays, this makes the accretion disk a powerful tool for astronomers to study black holes, as the radiation they emit provides clues about the mass, spin, and orientation of the black hole it surrounds. The shape of the accretion disk is not uniform. It's often thick and puffed up on the outer edges, where the matter is cooler and less dense. As the matter spirals inward, it becomes compressed, heated, and flattened into a razor-thin disk. The inner edge of the disk is a place of extremes. It's here that the orbital speeds approach a significant fraction of the speed of light, and the temperatures are at their highest. The material at the very inner edge of the disk is so close to the black hole that the immense gravitational pull begins to warp spacetime itself. This leads to bizarre relativistic effects, such as the bending of light, which can cause the black hole to appear as a dark, distorted shadow against the brilliant backdrop of the accretion disk. These jets and the radiant winds act like a galactic scale sandblaster. They can plow through the galaxy's interstellar gas, heating it up and blowing it right out of the galaxy. This has a negative feedback effect by removing the cold gas. The black hole shuts down star formation in the galaxy, effectively starving itself and regulating its own growth. It keeps the galaxy from getting too big, too fast. In some cases, the pressure from these jets can also compress nearby gas clouds, triggering a burst of new star formation, a positive feedback. This intricate dance, this feedback loop between the central engine and its galactic host, is now believed to be one of the most fundamental processes in shaping the universe as we see it today. The story of the supermassive black hole has taken us from tracking the subtle dance of stars in our own backyard to imaging the edge of infinity in distant galaxies. We have found them to be not cosmic aberrations, but fundamental components of the universe. They are the giants that lurk in the dark, with masses that defy easy comprehension and densities that break the laws of conventional physics. They are the engines of the quasars, the brightest beacons in the cosmos. Their origin remains one of the great unsolved puzzles, a story whose first chapters are only now being read by our most powerful telescopes. But most importantly, we have learned that they are the reigning monarchs of their domains. Through a delicate and violent process of feedback, these central black holes are inextricably linked to the fate of their host galaxies. They are the beating hearts that pump energy into the galactic ecosystem, governing the rhythm of stellar birth and death. The silent dark point at the center of a galaxy is not an end. It is the architect, the regulator, and the ruler of its glittering, spinning kingdom. The term black hole evokes a singular image, a monstrous dark sphere from which nothing can escape. Yet, in the vast and varied cosmos, this simple term hides a rich complexity. A black hole is defined not by what it is, but by what it does. It is a region of spacetime where gravity is triumphant. But the story of how such a region comes to be can follow two vastly different paths. This is a tale of two black holes, a cosmic detective story with two very different suspects that die in one corner. We have the known perpetrator, the usual suspect, whose life and death we have pieced together through decades of observation. This is the Stellama's black hole, born from fire and fury in the spectacular death of a giant star. In the other corner, we have the elusive phantom, a suspect from the dawn of time itself, a creature of theory and conjecture whose existence could solve some of the deepest mysteries of the universe. This is the primordial black hole. One is a known player in the cosmic drama. The other is a ghost that may or may not be haunting the stage. By comparing them, we explore the breathtaking scope of what a black hole can be. From the predictable to the profoundly strange, the story of a stellar mass black hole is the final dramatic chapter in the life of a very large star. Imagine a star at least 20 to 25 times more massive than our Sun. For millions of years, it lives in a state of glorious equilibrium. Deep in its core, the crushing force of its own gravity squeezes atoms together, fueling nuclear fusion. This fusion releases a tremendous outward pressure of energy and radiation. The star is a battlefield with the inward crush of gravity perfectly balanced by the outward blast of a continuous nuclear explosion. But this balance cannot last. Eventually, the star burns through the fuel in its core. The fusion engine sputters and dies. Suddenly, the outward pressure vanishes. With nothing to hold it up, gravity wins. In an instant, the star's core implodes upon itself with unimaginable violence. The outer layers, no longer supported, come crashing down onto the collapsing core, only to rebound in one of nature's most spectacular events, a supernova explosion. For a few weeks, the dying star can outshine its entire galaxy, blasting its outer layers across space as a beautiful expanding nebula. While the outer layers are ejected, the core continues to collapse. If the original star was massive enough, the remnant core will be heavier than about 3 times the mass of our Sun. At this point, no known force in nature can halt the collapse. It crushes past the density of an atomic nucleus, past the state of a neutron star, and continues to collapse indefinitely toward a single point of infinite density, a singularity. An event horizon forms around this point, sealing it off from the rest of the universe. A stellar mass black hole is born. This life story gives the stellar mass black hole a very specific profile mass. Its mass is dictated by the star that created it. This gives it a well-defined range, typically from about 3 to 100 times the mass of our Sun. It cannot be lighter than about 3 solar masses, as a smaller core would stabilize as a neutron star or white dwarf location, since they are born from massive stars. They are found where massive stars live and die scattered throughout the plane of galaxies, like our Milky Way. We often find them in binary systems, orbiting a companion star from which they can siphon material, creating intensely bright sources of X-rays. The evidence for their existence is overwhelming and direct. We've detected the X-rays from their superheated accretion disks for decades in objects. Like the famous Cygnus X1, we have tracked stars orbiting them, and most spectacularly since 2015, the LIGO and Virgo observatories have directly detected the gravitational waves, ripples in the fabric of spacetime that are emitted when 2 stellar black holes spiral into each other and merge. They are a confirmed and fundamental part of our cosmic landscape, the elusive phantom, a relic of the Big Bang. Now, let us rewind the clock, not by millions of years, but by 13.88 billion years, to the very first second of the universe's existence. There are no stars, no galaxies, only a thing, unimaginably hot and dense plasma, expanding rapidly from the Big Bang. This primordial soup was not perfectly smooth. Quantum mechanics dictates that it would have been filled with tiny, random fluctuations in density. Some regions, slightly denser and hotter than others, die in the 1970s. Physicists Yakov Zeldovich and Stephen Hawking realized the profound implication of this. In the standard model of stellar collapse, gravity has to overcome the immense outward pressure of nuclear fusion. But in the early universe, there was no such pressure fighting back. They proposed that if a region was by chance sufficiently denser than its surroundings, its own gravity could cause it to collapse directly and immediately into a black hole. This is the birth of a primordial black hole, PBH. It is not the child of a dead star. It is a relic of the universe's fiery birth. This completely different origin story gives the PBH a radically different profile mass. This is the most critical distinction. A PBH's mass is not tied to the physics of a star. It depends only on the size and density of the initial fluctuation. In the early universe, this means PBHs could theoretically have any mass. They could have formed with the mass of a large asteroid 10 of 1 kilogram, a mountain, the moon, or even a planet. At the other extreme, They could have formed with thousands or even millions of solar masses far too large to have come from a single star location. Since they were formed before galaxies even existed, they would not be confined to the galactic disk. They would be ancient wanderers populating all corners of the universe, including the vast spherical galactic halo that surrounds the main disk of our galaxy. They would be everywhere, hiding in plain sight evidence. Despite decades of searching, the evidence for their existence is precisely zero. They remain a compelling but entirely hypothetical entity. A more advanced and equally speculative idea involves manipulating the fabric of space-time itself. In theory, a sufficiently advanced civilization might be able to create a device that could warp space-time around a black hole. This device could, for example, create a temporary bubble of flat space-time around the event horizon, allowing an object to cross it without being trapped. This would require an immense amount of energy and a level of technological mastery far beyond anything we can concurrently imagine. Another concept is to use the energy of the black hole itself. The immense rotational energy of a spinning black hole could theoretically be harnessed. This is known as the Penrose process. While it doesn't allow for escape from inside the event horizon, it suggests that a spacecraft could be slingshot around a spinning black hole to extract energy and achieve immense speeds, potentially aiding in a close call escape from its gravitational pull before crossing the event horizon. Point 4. A new theory of gravity. All these ideas are based on our current understanding of general relativity. However, general relativity is known to break down at the singularity of a black hole. It's possible that a new, more complete theory of gravity, such as quantum gravity, would provide a different picture of a black hole's interior. This new theory might reveal that the singularity is not a point of infinite density, but rather something else entirely, and that the one-way street of the event horizon is not as absolute as we currently believe. In conclusion, while the laws of physics as we know them make escaping a black hole impossible, the hypothetical ideas of wormholes, Hawking radiation, space-time manipulation, and a new theory of gravity offered tantalizing glimpses into what might be possible under conditions that are currently beyond our reach. For now, a black hole remains the ultimate cosmic trap, a one-way trip to oblivion. Black holes in science fiction versus reality. Black holes are a source of endless fascination for both scientists and storytellers. They are cosmic voids of immense power, making them a perfect plot device for science fiction. However, the black holes depicted in movies and books often differ wildly from the reality described by physics. Let's explore some of the key differences between how black holes are portrayed in science fiction and how they behave in the real universe. Science fiction, a cosmic vacuum cleaner. In many sci-fi stories, black holes are portrayed as cosmic vacuum cleaners, sucking in anything and everything that gets too close. Spaceships are often seen being pulled inexorably toward a black hole from vast distances, like a drain pulling. In reality, a black hole is no more of a cosmic vacuum cleaner than a star. Its gravitational pull is powerful, but it's not a magical force that sucks things in. From a safe distance, the gravity of a black hole is the same as any other object of the same mass. For example, if our sun were to instantly become a black hole, the Earth would not be sucked in. it would continue to orbit the black hole at the same distance in the same orbit, because the mass of the black hole would be the same as the mass of the sun. You would, however, get very cold very quickly. The sucking effect only becomes extreme when an object gets very, very close to the event horizon. Science fiction, visible voids and portals. Sci-fi often portrays black holes as visible, swirling funnels, or portals to other dimensions. They are sometimes depicted as having a clear, definable surface that can be seen from a far reality. A black hole itself is invisible. It's an absence of light, a region of spacetime from which no light can escape. What we can see is the accretion disk, the superheated gas and dust swirling around the black hole. This disk glows brilliantly across the electromagnetic spectrum, and it's what we see in real-life images, like the one from the Event Horizon Telescope of the M87 black hole. The dark central region is not the black hole itself, but its shadow. Against the glowing backdrop of the accretion disk, science fiction, a quick and painless end in some movies. Falling into a black hole is a quick and clean death. A spaceship or character might disappear in a flash of light, with no mention of the bizarre physics at play. Reality. The end for an object falling into a black hole would be anything but quick and clean. The intense gravitational forces would cause a phenomenon known as spaghettification. As an object approaches the black hole, the side closer to the black hole experiences a much stronger gravitational pull than the side farther away. This difference in gravity, known as tidal force, would stretch the object out like a piece of spaghetti, tearing it apart atom by atom. This would happen long before the object ever reached the singularity. Science fiction, time travel, and time warps. Time travel and time dilation are often key elements in sci-fi stories, involving black holes where characters can travel forward in time by orbiting a black hole reality. This part of science fiction is actually rooted in real physics. According to general relativity, gravity warps spacetime, and this includes the flow of time. Time slows down in the presence of a strong gravitational field. For an observer far away, a clock near a black hole would appear to tick more slowly. This effect is known as gravitational time dilation. The closer you get to a black hole, the more extreme this effect becomes. This is not a form of time travel, but it is a real and measurable effect. However, the time dilation we've measured on Earth is minuscule, and to experience a significant effect, you would have to be dangerously close to a black hole. Science fiction, using black holes as energy sources or weapons. Some sci-fi shows feature advanced civilizations using the immense energy of a black hole for power or as a superweapon. Reality. While it's true that black holes are some of the most powerful objects in the universe, harnessing their energy is a theoretical concept. The Penrose process suggests it's possible to extract rotational energy from a spinning black hole. But this is a highly speculative idea. Using a black hole as a weapon is an even more far-fetched concept, as the energy released from a black hole merger, while immense, is not something that could be controlled or directed in the way a weapon would need to be. In conclusion, while science fiction provides a compelling and often visually stunning narrative for black holes, the reality is far more complex and mind-bending. The true nature of black holes, their invisible nature, the bizarre effects of spaghettification, And the warping of time and space is more intriguing than any fiction could invent. The accretion disk is not a passive structure. It's a dynamic and violent system. It's a cosmic engine that powers some of the most spectacular phenomena in the universe, such as quasars and active galactic nuclei, AGN. These are supermassive black holes at the centers of galaxies that are actively feeding. The immense energy released by their accretion disks can produce jets of matter that are launched from the poles of the black hole at nearly the speed of light. These relativistic jets can extend for hundreds of thousands of light years, carving out vast bubbles in the intergalactic medium. The jets are so powerful that they can influence the evolution of their host galaxies, triggering or suppressing star formation. The study of accretion disks is crucial for understanding black holes. They are the only way we have to observe black holes directly. The light and radiation we see from an accretion disk tell us about the black hole's mass, spin, and orientation. The temperature and brightness of the disk are related to the rate at which the black hole is feeding. By studying the spectra of the light from the disk, astronomers can determine the composition of the matter and the speed at which it is orbiting. This information is vital for testing theories of gravity and understanding the fundamental properties of black holes. The journey of matter through the accretion disk is a one-way trip, a relentless spiral toward a point of no return. As the matter gets closer and closer to the black hole, the gravitational forces become overwhelming. Eventually, the matter crosses the event horizon, the point beyond which nothing, not even light, can escape. At this point, the matter is lost to our universe forever. The energy it released in its final moments of existence is all that remains as a testament to its fate. The existence of accretion disks has been confirmed by a wealth of observational evidence. We've seen them in action around stellar mass black holes in our own galaxy and around supermassive black holes in distant galaxies. The first ever image of a black hole captured by the Event Horizon Telescope (ET) collaboration was of the supermassive black hole at the center of the galaxy, M87. This image clearly shows the black hole shadow silhouetted against the bright, lopsided ring of its accretion disk. This landmark achievement provided direct visual evidence for the existence of black holes and their accretion disks, and it was a stunning confirmation of Einstein's theory of general relativity. The image showed a glowing ring-like structure with a central dark region, which is the shadow of the black hole itself. The brightness of the ring is not uniform. One side is much brighter than the other. This is due to the relativistic beaming effect, where the light from the side of the disk moving toward us is boosted in brightness, while the light from the side moving away from us is dimmed. This is a powerful demonstration of the extreme physics at play near a black hole. The process of accretion is not unique to black holes. It also occurs around other massive objects, such as neutron stars and white dwarfs. However, the extreme gravitational forces and the unique physics of a black hole make the accretion disks around them particularly powerful and spectacular. In these disks, the matter is heated to temperatures so high that it emits X-rays and gamma rays, making them powerful sources of high-energy radiation. This is how we first detected many black hole candidates, by observing the intense X-ray emissions from their accretion disks. The study of accretion disks is an active and exciting field of research. There are still many unanswered questions. For example, how does the angular momentum of the matter get transported outward, allowing the matter to spiral inward? What is the exact mechanism that powers the relativistic jets? How do accretion disks influence the growth and evolution of galaxies? These are just some of the questions that astronomers are trying to answer by studying the light and radiation from these cosmic whirlpools. Conclusion. The accretion disk is a beautiful and violent structure, a cosmic vortex of matter swirling toward its ultimate doom. It is the final stage in the life of a star or a cloud of gas, a journey that ends in the ultimate gravitational well of a black hole. It is a powerful engine of energy, a beacon in the darkness, and our only window into the mysterious and invisible world of black holes. It's a testament to the power of gravity and the extreme physics that govern the most massive and mysterious objects in our universe. It is a place where matter, light, and space-time are pushed to their limits, where the laws of physics, as we know them, are stretched and distorted, and where the final chapter of a cosmic story is written in fire and light. It's a place of incredible power and beauty, a cosmic dance of destruction that gives birth to some of the most spectacular phenomena in the cosmos. The accretion disk is the beginning of the end, the final brilliant act before the curtain of the event horizon falls forever. Black holes and gravitational waves. The very existence of black holes, as predicted by Einstein's theory of general relativity, is a testament to the profound nature of gravity. This theory describes gravity not as a force, but as a curvature of space-time caused by the presence of mass and energy. A black hole is the most extreme manifestation of this idea. A region where space-time is so intensely warped that nothing, not even light, can escape. The story of how black holes and gravitational waves are intertwined is a tale of cosmic violence and triumph. It's a story of two of the universe's most mind-bending phenomena, and the journey to prove their connection, that a black hole is formed when a massive star, several times more massive than our sun, exhausts its nuclear fuel. The outward pressure from fusion that had been holding the star up against its own gravity ceases, and the star undergoes a catastrophic gravitational collapse. The stellar core implodes, crushing itself into an infinitely dense point called a singularity. The collapse is so complete that the gravitational field becomes unimaginably strong, creating the black hole and its event horizon, the point of no return. For a long time, black holes were purely theoretical objects, their existence inferred from the bizarre behaviors of objects around them, such as the swirling accretion disks we've already discussed. The direct observation of a black hole's gravity in action was a challenge that seemed impossible. This is where gravitational waves come in. Just as a charged particle accelerating produces ripples in the electromagnetic field, light massive objects accelerating and moving violently produce ripples in the fabric of space-time itself. These ripples are gravitational waves. They travel at the speed of light, carrying with them information about their cataclysmic origins. Einstein predicted the existence of gravitational waves in 1916, but he believed they would be too weak to ever be detected. The changes in space-time they would cause were thought to be infinitesimally small. Imagine a wave from a ship on the ocean. It's a significant disturbance. Now imagine that same wave traveling for billions of light years. By the time it reaches us, it's a tiny ripple. Similarly, a gravitational wave from a cosmic event would stretch and compress spacetime by a fraction of the width of an atom. The events that create these waves must be incredibly energetic and involve massive objects moving at high speeds. The most promising candidates for producing detectable gravitational waves were binary systems of massive objects, such as two black holes or two neutron stars orbiting each other. As these objects spiral inward toward a final violent merger, they radiate gravitational waves, losing energy and causing their orbit to shrink. This process, known as in spiral, is a cosmic death spiral that ends in a colossal collision. In 2015, the unimaginable happened. The Laser Interferometer Wave Observatory, LIGO, an incredibly sensitive detector, made a groundbreaking discovery. On September 14, 2015, LIGO detected a signal that was a chirp, a characteristic, rising tone, lasting for a fraction of a second. This chirp was the fingerprint of two black holes, one roughly 36 times the mass of the Sun, and the other 29 times the mass of the Sun, that had merged into a single, larger black hole of 62 solar masses. The missing 3 solar masses were converted into a burst of gravitational wave energy in a process so powerful that for a fraction of a second, the energy released was more than all the stars in the observable universe combined. This discovery, known as GW150914, was the first ever direct detection of gravitational waves and the first direct observation of a black hole merger. It confirmed 2 of Einstein's key predictions at once: the existence of gravitational waves and the existence of black holes in binary systems. It opened a new window into the universe, allowing us to hear the cosmos in a way we never could before. Before this, all of our astronomical observations were based on electromagnetic radiation, light, radio waves, X-rods, etc. Now, we could observe the universe through the sound of spacetime itself. The detection of gravitational waves from merging black holes is more than just a confirmation of a theory. It's a new way of doing astronomy. Gravitational waves can pass through matter and radiation unimpeded, giving us a clear view of the most extreme events in the universe that would otherwise be hidden from us. We can now study black holes as they form and merge, a process that is invisible to traditional telescopes since that first detection. LIGO and its sister observatory, Virgo, have detected dozens of similar events, including merges of black holes and even the merger of 2 neutron stars. The neutron star merger, GW170817, was particularly significant. The event produced a powerful flash of light, a kilonova, and confirmed that the merging of neutron stars is a primary source of heavy elements like gold and platinum. This event was a turning point, ushering in the era of multi-messenger astronomy, where we can observe a cosmic event with both gravitational waves and electromagnetic radiation. The future of gravitational wave astronomy is bright. Scientists are planning and building even more sensitive detectors, and eventually a space-based detector called LISA Laser Interferometer Space Antenna. LISA will be able to detect the gravitational waves from supermassive black hole merges, which are much lower in frequency and last for much longer than the events LIGO can detect. This will allow us to study the growth of these behemoths at the centers of galaxies and shed light on how galaxies themselves evolve. The dance of two black holes in their final moments is a cosmic ballet of immense power. It's a spectacular example of gravity at its most extreme, a dance that ends in a ripple that travels across the universe. A message from the deep cosmos telling us about the most profound and violent events in the history of our universe. The detection of these gravitational waves is not just a scientific achievement, it's a profound moment in our human history, a moment when we began to truly listen to the universe. The discovery of gravitational waves from black hole merges has validated Einstein's general relativity in a way that he could have never imagined. It has opened up a new frontier in physics and astronomy, allowing us to explore the most violent and mysterious corners of the cosmos. It's a testament to human ingenuity and our endless curiosity, a journey that began with a theoretical prediction and culminated in a direct observation that changed our understanding of the universe forever. Observational evidence: how we detect black holes. Black holes are by their very nature invisible. They are regions of spacetime from which nothing, not even light, can escape. So, if we can't see them directly, how do we know they exist? The answer lies in the dramatic and violent effects they have on their surroundings. Astronomers use a variety of clever and indirect methods to detect the presence of these enigmatic objects. From observing the intense radiation of matter spiraling into them to the ripples they create in the fabric of spacetime, the search for black holes is a cosmic detective story, with each piece of evidence providing a clue to their existence and properties. Point 1 X-ray emission from accretion disks. One of the most powerful pieces of evidence for black holes comes from observing X-rays. When a black hole is actively feeding on a nearby star or gas cloud, it forms an accretion disk, a swirling vortex of superheated matter. The friction and compression within this disk heat the gas to millions of degrees, causing it to emit immense amounts of X-rays. These X-rays are a telltale sign of a black hole, as they are not produced by normal stars. Astronomers use specialized X-ray telescopes in space, like the Chandra X-ray Observatory and the NUS satellite, to detect these emissions. By studying the properties of the X-rays, such as their intensity and spectral signature, we can infer the properties of the black hole itself, including its mass and spin. We've detected thousands of these X-ray binaries, providing a rich catalog of stellar mass black hole candidates in our own galaxy and beyond. The very first black hole candidate, Cygnus X1, was discovered this way. It's a binary system where a massive blue star orbits a compact, invisible object that emits powerful X. The mass of the invisible object was calculated to be too large to be a neutron star, making a black hole the only plausible explanation. Point 2. Gravitational waves from merges, as discussed previously. The direct detection of gravitational waves from merging black holes has provided a refutable evidence of their existence. These ripples in spacetime are the ultimate proof, a direct signal from the black holes themselves as they collide. The Laser Interferometer Gravitational Wave Observatory, LIGO, and its collaborators have detected dozens of such mergers. The chirp signal they pick up not only proves the black holes are real, but also gives us incredibly precise information about their masses. spins, and the energy they radiate during the final moments of their cosmic dance. This opened up a new way of seeing the universe, and it has already revolutionized our understanding of black hole formation and evolution. 3. Stellar orbits and dynamics. We can infer the presence of a supermassive black hole at the center of a galaxy by observing the movement of stars and gas around it. Stars orbiting a massive, invisible object at the center of a galaxy will move at extremely high speeds by applying Kepler's laws of planetary motion, which relate an object's orbital speed to the mass of the central body. Astronomers can calculate the mass of the central object. This is exactly how we confirmed the existence of the supermassive black hole at the center of our own Milky Way galaxy, Sagittarius, a star. For over 2 decades, astronomers observed the orbits of stars in the galactic center. One star, S2, orbits the central object at incredible speeds, completing a full orbit in just 16 years. Its orbit is so tight that it passes within a few billion miles of the black hole, a cosmic hair's breadth. By tracking its movement, scientists calculated the mass of the central invisible object to be about 4 million times the mass of the Sun. The sheer density of this mass in such a small space means it can only be a supermassive black hole. 4. Gravitational lensing. The intense gravity of a black hole can warp spacetime to such a degree that it bends the path of light from objects behind it. This phenomenon is called gravitational lensing. A black hole acts like a giant lens, distorting and magnifying the light from distant stars or galaxies. While we haven't yet directly observed lensing by a single black hole, we have seen it on a larger scale with galaxy clusters and have observed the effects of strong gravity near black holes. The famous image of the M87 black hole captured by the Event Horizon Telescope, EHT, is a perfect example. The image doesn't show the black hole itself, but its shadow cast against the backdrop of its glowing accretion disk, the ring of light, is the result of extreme gravitational lensing, where photons from the back of the disk are bent around the black hole and into our line of sight. This image was the first direct visual evidence of a black hole and a stunning confirmation of Einstein's theory of general relativity in an extreme gravitational environment. The resolution of the paradox is still a topic of intense research, but the scientific community has largely moved toward the idea that information is in fact preserved. Hawking himself later conceded this point in 2004, a move that was hailed as a major step forward. While we don't yet have a complete picture of how the information is preserved, some theories suggest that subtle correlations and quantum entanglement between the escaping Hawking radiation particles might carry the information. The information paradox is not just an abstract philosophical problem. Its resolution holds the key to a deeper understanding of the universe, potentially leading to a unified theory of quantum gravity that can reconcile general relativity and quantum mechanics. It's a testament to the incredible power of black holes as cosmic laboratories, pushing our understanding of physics to its absolute limits and forcing us to confront the very nature of reality. Quasars are among the most luminous objects in the universe. These are powered by supermassive black holes at the centers of galaxies that are voraciously consuming matter. The accretion disks around these black holes are so hot and bright that they can outshine an entire galaxy of stars. The energy released can also produce powerful relativistic jets that shoot out from the poles of the black hole at nearly the speed of light. While observing these quasars and other active galactic nuclei, AGN astronomers can study the properties of the supermassive black holes at their cores. The brightness of the quasar is directly related to the mass of the black hole and the rate at which it is feeding. The jets provide clues about the black hole spin and the magnetic field surrounding it. These observations have shown that nearly every major galaxy has a supermassive black hole at its center, playing a crucial role in galaxy evolution. In summary, while black holes are inherently dark, their effects on the universe are anything but. The observational evidence for their existence is overwhelming, coming from a variety of sources and methods. From the scorching hot glow of their accretion disks to the gentle ripples they send through spacetime, black holes leave their fingerprints all over the cosmos. The ongoing quest to understand them continues to push the boundaries of physics and astronomy, revealing a universe that is far stranger and more beautiful than we ever imagined. Escape velocity, and why nothing can outrun it. To understand a black hole, you must first understand the concept of escape velocity. Escape velocity is the minimum speed an object needs to escape the gravitational pull of a massive body. Imagine throwing a ball into the air. The faster you throw it, the higher it goes before gravity pulls it back down. If you could throw the ball fast enough, it would completely escape Earth's gravity and fly into space. The speed required to do this is Earth's escape velocity, which is about 11.22 kilometers per second, about 25,000 miles per hour. Every celestial body has an escape velocity. The more massive and compact the body, the stronger its gravity and the higher its escape velocity. For instance, the escape velocity from the surface of our Sun is a staggering 618 kilometers per second. This is already an immense speed, but for a black hole, the escape velocity becomes the ultimate limit that a black hole is formed. When an object is so dense that its gravitational pull is extreme, as an object's mass is compressed into an incredibly small space, the escape velocity at its surface increases dramatically. The theoretical physicist John Wheeler coined the term black hole to describe this object, which is so dense that its escape velocity exceeds the speed of light. This is the key to understanding a black hole. The speed of light c is the universal speed limit. Nothing with mass can travel at this speed, and nothing can travel faster. Light, being massless, travels at this speed. Since a black hole's escape velocity is greater than c, not even light can escape its gravitational pull. This is why black holes are black. Any light that falls into them is trapped forever. The region around a black hole where the escape velocity equals the speed of light is called the event horizon. The event horizon is not a physical surface. It's a boundary in spacetime. Once an object or even a photon of light crosses this boundary, it is on an irreversible journey toward the singularity at the black hole center. The term event horizon is apt because any event that occurs inside this boundary can never be observed from the outside. The information from that event, including light and matter, is lost to the universe forever. The size of the event horizon, known as the Schwartz radius, depends on the mass of the black hole. The more massive the black hole, the larger its event horizon. For example, a black hole with the mass of our Sun would have a Schwarzschild radius of about 3 kilometers. If you could compress the Earth into a black hole, its radius would be less than a centimeter. This highlights how incredibly dense these objects are inside the event horizon. The laws of physics, as we know them, are taken to their extremes. Space-time is so severely curved that all paths lead inextricably toward the central singularity, a point of infinite density where all of the black hole's mass is concentrated. At this point, our current understanding of physics, including general relativity, breaks down. We need a theory of quantum gravity to describe what happens at the singularity. The concept of escape velocity shows why nothing, not even a highly advanced spacecraft, could ever outrun a black hole once it has crossed the event horizon. To do so would require traveling faster than the speed of light, which is fundamentally impossible according to Einstein's theories. This makes a black hole a one-way trip, a cosmic trap from which there is no return. This isn't just a hypothetical concept. We see the effects of this extreme gravity in the universe. The bending of light around a black hole, known as gravitational lensing, is a direct consequence of space-time curvature. The fact that we can't see the black hole itself, but only its effects on the light and matter around it, is the most profound proof of this universal speed limit and the unstoppable nature of gravity at its most extreme hypothetical ways to escape a black hole. The idea of escaping a black hole is a staple of science fiction. But in reality, it's a monumental challenge that pushes the boundaries of our understanding of physics. According to Albert Einstein's theory of general relativity, once an object crosses the event horizon, escape is impossible. The event horizon is the point of no return, a boundary in spacetime where the escape velocity exceeds the speed of light. Since nothing can travel faster than light, anything that crosses this threshold is trapped forever. However, theoretical physicists and science fiction writers have explored several hypothetical and highly speculative ideas that might, under specific conditions, allow for an escape. These ideas often involve a radical departure from our current understanding of physics or a manipulation of exotic phenomena. One, traversable wormholes. One of the most popular and intriguing concepts is the existence of a wormhole. A wormhole is a theoretical shortcut through spacetime connecting to distant points. While general relativity allows for the existence of wormholes, they would likely be unstable and would collapse instantly. To keep one open and traversable, it would require the use of exotic matter with negative energy density that, in the context of black holes, a wormhole could theoretically provide an escape route. Instead of leading to a singularity, a black hole might be the entrance to a wormhole that exits in another part of the universe, or even in another universe entirely. However, the existence of such matter and the stability of these wormholes are purely speculative. The journey through a wormhole would also likely be fraught with danger, as the immense gravitational forces and tidal effects could tear an object apart. Point to Hawking radiation and information paradox. Another theoretical escape route relates to the work of physicist Stephen Hawking. He proposed that black holes aren't completely black, but instead slowly emit radiation, now known as Hawking radiation. This radiation is a quantum mechanical effect that occurs just outside the event horizon. Over an incredibly long time, a black hole would evaporate due to this process. The idea of escaping a black hole through Hawking radiation is not about a physical object leaving, but rather about the information it contained. This ties in to the black hole information paradox, which asks what happens to the information of objects that fall into a black hole. Does it get destroyed, or is it preserved in some form? Hawking suggested that the information might be encoded in the subtle properties of the Hawking radiation. If this is true, then while you would be physically destroyed, your information might escape and eventually re-emerge in a different, highly scrambled form. However, this is still a major unresolved question in physics, and it does not provide a practical way to physically escape. However, from your perspective as the astronaut, the story is far more chilling. You would continue to fall toward the event horizon and cross it without any sensation of slowing down. But once you've crossed, a truly bizarre shift occurs. The outside universe, which was once a constant backdrop, now begins to speed up. You would witness the entire future of the universe outside the black hole unfold in an instant. The deaths of stars, the birth of new galaxies, the eventual heat death of the universe. All of it would be a flash, a final, incomprehensible spectacle as you plunge toward the singularity. This is the ultimate end of time for an observer. The concept of time dilation near a black hole isn't just a fascinating thought experiment. It's a profound challenge to our intuitive understanding of reality. It shows us that time is not a universal constant, but is relative, intimately linked to the gravity and motion of the observer inside the event horizon. Theoretical possibilities. What happens after you've crossed the point of no return? You've already experienced the unsettling effects of time dilation, the bizarre bending of light, and perhaps the violent stretching of your body. But now you are inside the event horizon, a place where the familiar rules of the universe are turned upside down. This is a realm we can only explore through theoretical physics, a place of profound mystery where our understanding of space and time is pushed to its absolute limits. Once inside the event horizon, space and time effectively switch roles. In our everyday world, we can move freely through space, back and forth, up and down, but we are inexorably carried forward through time. Inside the black hole, this is reversed. You can't move back out any more than you can move back yesterday. The forward direction of time, your unavoidable future, is now the singularity. You are on a one-way trip, a collision course with a point of infinite density from which there is no escape. The universe you left behind is now a fleeting moment in your past, forever out of reach. The journey inside is marked by extreme distortions. The light from the stars and galaxies outside the black hole would be compressed and blue-shifted, appearing as a single blinding point of light behind you. But this light wouldn't last. It would be a fleeting spectacle as you plunge deeper. The gravity is so intense that light can't escape, meaning the inside of the black hole is a region of utter darkness, illuminated only by the light that has fallen in with you. For the intrepid, or perhaps unfortunate traveler, the experience would be terrifyingly alien. In this region of extreme curvature, the traditional concepts of up and down or left and right lose their meaning. All directions in space point toward the singularity. It's an environment where the geometry of the universe itself is no longer flat or even gently curved, but is instead warped into a shape that is almost impossible to visualize. However, the nature of what lies inside the event horizon is still a subject of intense debate and speculation. Our current models, based on general relativity, predict a singularity where the laws of physics break down. But many physicists believe that something else must happen. The idea of a point of infinite density seems unphysical, a sign that our theory is incomplete. One of the leading theoretical alternatives comes from string theory, which proposes that the singularity is not a point, but a fuzzy ball of strings. This fuzzball would be a dense, tangled mess of fundamental strings, and it would not have a true singularity at its center. Instead, the fuzzball would have a finite size and density, and the laws of physics would still apply. In this model, the event horizon is a more complex surface, and there might not even be a true inside and outside in the traditional sense. Another theory, loop quantum gravity, suggests that spacetime itself is quantized or made up of tiny, discrete units. In this view, there's a minimum size that space can be, which would prevent matter from being crushed into an infinitely dense point. The singularity would be replaced by a region of extremely high but finite density, where the fabric of spacetime is compressed to its smallest possible scale. Then there's the truly bizarre idea of a white hole. Some solutions to Einstein's equations suggest that black holes and white holes are two sides of the same coin. A white hole is a hypothetical object that is the reverse of a black hole. Matter and light can escape from it, but nothing can enter. Some physicists speculate that the singularity inside a black hole could be connected to a white hole in another part of the universe, or even in another universe entirely. This would mean that a black hole could be a portal to a new cosmic destination, a sort of cosmic recycling center. While this is a highly speculative idea, it's a tantalizing glimpse into the wild possibilities that lie beyond our current understanding. Ultimately, what happens inside the event horizon remains one of the greatest unsolved mysteries in science. It's a place where our best theories break down and new, more complete theories are waiting to be discovered. It's a frontier of knowledge, a place where the universe challenges us to think beyond the limits of our current understanding. The role of general relativity in understanding black holes. The concept of a black hole, a region of space where gravity is so strong that nothing, not even light, can escape, might sound like the wild fantasy of a science fiction writer. But the theoretical foundation for this mind-bending idea was laid over a century ago by one of the greatest minds in history, Albert Einstein. In his theory of general relativity, published in 1915, this theory revolutionized our understanding of gravity and became the indispensable tool for comprehending the existence and nature of black holes. Before general relativity, Isaac Newton's law of universal gravitation had been the undisputed champion for over 2 centuries. Newton's theory worked brilliantly for describing the orbits of planets and the fall of an apple, but it treated gravity as a simple force, a mysterious, instantaneous pull between 2 objects. Einstein's breakthrough was to see gravity not as a force, but as a consequence of the curvature of spacetime. Imagine spacetime as a giant, flexible trampoline. An object with mass, like a star or a planet, sits on the trampoline, creating a dip or a curve. The more mass of the object, the deeper the curve. When a smaller object, like a marble, rolls by, it doesn't get pulled toward the star. Instead, it follows the curve in the trampoline created by the star's mass. This is how general relativity explains orbits. Planets are simply following the curves in spacetime created by the sun's enormous mass. A black hole is the ultimate expression of this idea. It's an object so incredibly dense that it punches a hole in the fabric of spacetime, creating a point of infinite curvature, the singularity. The warping of spacetime around a black hole is so extreme that it creates a one-way street. The curvature is so steep that once you've fallen into the hole, there's no way to climb back out. No matter how fast you travel, even light, the fastest thing in the universe, is unable to escape this gravitational well, which is why we call them black. A black hole is an object with such immense gravitational pull that nothing, not even light, can escape it. This gravitational force is so strong because a huge amount of matter has been squeezed into a tiny space. This could happen at the end of a star's life, the event horizon, the point of no return. Imagine a cosmic whirlpool, a drain in the fabric of spacetime with an invisible boundary marking the point from which there's no return. This boundary is the event horizon, a term that sounds like something out of a science fiction movie, but in reality, it's a fundamental and terrifyingly real concept in physics. It's not a physical surface. You wouldn't feel or see a solid wall as you cross it. Instead, it's the point at which the escape velocity, the speed needed to break free from an object's gravitational pull, exceeds the speed of light, since nothing can travel faster than the speed of light. Once you cross this line, you are inevitably pulled toward the center of the black hole, the singularity. There's no turning back. The idea of the event horizon is a direct consequence of Albert Einstein's theory of general relativity, which posits that massive objects curve the fabric of spacetime. The more massive an object is, the more it warps. This fabric and a black hole is the ultimate example of this warping. The gravity is so intense that spacetime curves in on itself, creating a one-way street to the singularity. You can think of it like a waterfall. As you get closer to the edge, the water speeds up. The event horizon is the point where the water is moving faster than you can swim. So, you're inexorably carried over the edge. The size of the event horizon is directly proportional to the mass of the black hole. A small black hole formed from the collapse of a single star might have an event horizon just a few miles across. A supermassive black hole found at the center of most galaxies could have an event horizon larger than our entire solar system. This size, known as the Schwarz radius, is a crucial parameter in understanding the nature of a black hole. So what would it be like to approach and cross the event horizon? The experience would be profoundly different depending on the size of the black hole. For a small stellar mass black hole, the gravitational gradient would be incredibly steep. This means that the gravitational pull on your feet, if you were falling in feet first, would be much, much stronger than the pull on your head. This difference in gravitational force, known as tidal force, would stretch you out like a piece of spaghetti, a process charmingly, or perhaps chillingly, called spaghettification. You would be torn apart long before you even reach the event horizon. This violent fate is a direct result of the immense localized gravity of a small black hole. However, for a supermassive black hole, the situation would be much stranger. The event horizon is so vast that the gravitational gradient across your body would be negligible. You would cross the event horizon without feeling a thing. One moment you're an observer in a hostile yet navigable cosmic environment, and the next you're on a one-way trip to the center. It's a silent, serene, and utterly terrifying transition. From the outside, observers would see your clock slow down as you approach the event horizon, a phenomenon known as gravitational time dilation. Your light would become redder and dimmer, a process called gravitational redshift, until it fades away entirely at the event horizon. To them, it would look like you froze in time at the boundary, a ghost lingering at the edge of the abyss. But for you, the traveler, time would continue as normal. You would experience time at your own rate, watching the outside universe speed up, the light from distant galaxies becoming a blue-shifted blur as you plunge deeper into the black holes. Gravity. Well, inside the event horizon, the rules of physics as we know them are turned upside down. The directions of space and time are effectively swapped. The forward direction of time, which we normally perceive as a fixed and inexorable path, becomes a spatial direction pointing toward the singularity. You can't avoid moving toward the singularity any more than you can avoid moving forward in time. It's an inevitable fate. The universe outside the event horizon becomes a fleeting memory, a single point in the past that you can no longer reach or influence. Inside, there's only one future, the singularity. The event horizon isn't just a boundary in space. It's a boundary in information. According to the no-hair theorem, from the outside, we can only know three things about a black hole: its mass, its spin, and its electric charge. All other information about the matter that fell in, its chemical composition, its shape, its history, is lost forever. The hair of a black hole refers to any other properties it might have, but the theorem states that a black hole is bald, so to speak. This loss of information is a profound and controversial topic in physics, leading to the information paradox, a conflict between general relativity and quantum mechanics. The event horizon is the front line of this paradox, the place where information seems to vanish from the universe. So the event horizon is much more than just a point of no return. It's a cosmic frontier where the fundamental laws of the universe are pushed to their breaking point. It's a boundary that separates our familiar reality from a region where space and time are warped beyond recognition, where the future is a single point and where the past is forever out of reach. It's a testament to the extreme and beautiful weirdness of the cosmos, a place that embodies the very essence of a black hole's mystery and power. The event horizon is the ultimate symbol of the one-way nature of a black hole, a truly final frontier singularity where physics breaks down at the very heart of a black hole. Past the event horizon lies a point of infinite density and zero volume, the singularity. This is not a place you can visit or even imagine in the traditional sense. It's the point where all the mass of the black hole is crushed into an infinitesimally small space. Our current understanding of physics, particularly Albert Einstein's theory of general relativity, predicts the existence of this singularity. However, this same theory breaks down when trying to describe what happens at this point. leaving us with a profound mystery. General relativity tells us that the immense gravity of a black hole warps spacetime so severely that it creates a point of infinite curvature. The fabric of the universe is stretched and compressed to its absolute limit, a process that our equations simply can't handle. Think of it like this. If you were to draw a line on a stretched rubber sheet and then you started to press down on that sheet, the line would curve. A black hole is like an infinitely heavy object pressing down on the sheet of space-time, creating a hole that goes on forever. The singularity is the bottom of that hole, a place where all the known laws of physics cease to apply to. So, what does it mean for physics to break down? It means that our most trusted tools for understanding the universe no longer work. General relativity, which describes gravity on a large scale, and quantum mechanics, which describes the behavior of matter and energy on the smaller scales, are both essential for understanding what happens at the singularity. Yet, they are fundamentally incompatible. When you try to combine them to describe the extreme conditions at the center of a black hole, the mathematics produce nonsensical results, such as infinities. It's like trying to use a ruler to measure the distance. To a star, the tool isn't designed for the job. This is the great challenge of modern physics, the quest for a theory of quantum gravity. Such a theory would unite general relativity and quantum mechanics, giving us a new set of rules to understand the singularity and other extreme environments, such as the Big Bang. While physicists are working on several promising ideas, like string theory and loop quantum gravity, we don't have a complete theory yet. Therefore, the singularity remains a theoretical construct, a place where our current knowledge of the universe hits a wall. For a traveler falling into a black hole, the journey toward the singularity would be a one-way trip of increasing horror. As you cross the event horizon, space and time swap roles. The singularity, which was once a point in space, now becomes an inevitable moment in your future. You are pulled towards it with no possibility of escape. Everything you see, everything you know, becomes compressed and distorted. The light from the stars you left behind is stretched and shifted, becoming a blurry, blue-tinted memory. You are on a collision course with a point of infinite density, and there is no way to alter your course. As you get closer, the tidal forces would become absolutely overwhelming. While the event horizon of a supermassive black hole might be a serene crossing, the approach to the singularity is anything but. The difference in gravitational pull between your head and your feet would tear you apart atom by atom. The very fabric of your being would be unraveled, a process far beyond the simple spaghettification we discussed earlier. All the matter that makes up your body, and indeed all the matter that has ever fallen into the black hole, is crushed into this single mind-bending point. Dosso. What's inside the singularity? The truth is, we don't know. Our best theories suggest it's a point of infinite density where all the known laws of physics cease to exist. However, this is just what our current mathematics tell us. A future theory of quantum gravity might reveal something completely different. It's possible that the singularity isn't a point at all, but rather something else entirely. A fuzzball in string theory, for example, or a singularity black hole in loop quantum gravity. These theories offer alternatives to the infinitely dense point, but for now they remain unproven hypotheses. The singularity is the ultimate expression of a black hole's power and mystery. It is a place where gravity wins, where matter is annihilated and compressed, and where our scientific understanding is pushed to its absolute limit. It is the heart of darkness, the point of no return, and one of the most compelling and unsolved problems in all of physics, the tidal stretching effect. Imagine a cosmic bungee jump gone horribly wrong. You're falling toward a black hole, and as you get closer, you feel an intense pull, but it's not a simple tug. It's a difference in pull. The part of your body closest to the black hole is being yanked on with a force far greater than the part that's farther away. This isn't just uncomfortable. It's a catastrophic, body-shredding process. This is spaghettification, a vivid and scientifically accurate term for the tidal stretching effect that awaits anyone or anything that gets too close to a black hole. The term itself is a perfect description. You would be stretched out like a piece of spaghetti torn apart by the immense and uneven gravitational forces. This isn't science fiction. It's a direct consequence of the laws of physics. Tidal forces are caused by a difference in gravitational pull across an object. We experience this on Earth every day in a much milder form. The moon's gravity pulls on the side of the Earth, facing it more strongly than on the far side, creating the ocean tides we all know. But a black hole's gravity is so extreme and so localized that this difference in force becomes unimaginably powerful. The severity of spaghettification depends entirely on the size of the black hole. For a smaller stellar mass black hole, one that's only a few times more massive than our Sun, the gravitational pull becomes incredibly intense over a very short distance. This means the tidal forces are overwhelming and would rip you apart long before you even reach the event horizon. You wouldn't get a chance to cross the point of no return. Your fate would be sealed far beyond it, your atom scattering and joining the swirling chaos around the black hole. This is the brutal, violent end for any unsuspecting star or dust cloud that gets too close to a small black hole. However, the story is very different for a supermassive black hole, the kind found at the center of most galaxies. These giants are millions or even billions of times the mass of our Sun. Because of their immense size, their event horizons are also massive. This means the gravitational pull is much more uniform across a given distance. As a result, the tidal forces are much weaker at the event horizon. An astronaut falling feet first into a supermassive black hole might not feel any tidal stretching at all as they cross the boundary. The experience would be strangely calm and silent. They would cross the point of no return without a physical sensation, only to realize later that they are on an irreversible path toward the singularity. The spaghettification would still happen, but it would be delayed, occurring only as they got much closer to the infinitely dense core. So, for a stellar mass black hole, spaghettification is a lethal pre-horizon event. For a supermassive black hole, it's an equally lethal but posh horizon fate. The effect is the same, but the timing is radically different. This distinction is one of the most intriguing aspects of black hole physics, highlighting how a black hole's mass dictates the experience of falling into it. This process of tidal stretching is also a powerful tool for astronomers. When a star gets too close to a black hole, the immense tidal forces can rip the star apart. This event, known as a tidal disruption event, creates a brilliant flare of light and X-rays as the shredded stellar material heats up and swirls into the black hole's accretion disk. By observing these flares, scientists can indirectly study black holes and confirm their existence. The bright flash is a chilling cosmic signature, a testament to the destructive power of a black hole's gravity. Spaghettification isn't just a bizarre thought experiment. It's a vivid demonstration of the immense and non-uniform gravitational forces that define a black hole. It's a reminder that in the universe, a beautiful and calm-looking object can hold a terrible and destructive power-time dilation near a black hole in the vast and strange tapestry of the cosmos. One of the most mind-bending phenomena is the relationship between gravity and time. We've always thought of time as a constant, an unstoppable river flowing at a fixed rate for everyone. But near a black hole, that river slows to a crawl. This effect, known as gravitational time dilation, is not a trick of the mind or a theoretical guess. It is a direct and proven consequence of Einstein's theory of general relativity. Imagine you and a friend are on an interstellar journey. You're piloting a spaceship toward a black hole while your friend stays at a safe distance watching you from a powerful telescope. As you approach the black hole, its immense gravity begins to warp the fabric of space-time around you. From your perspective inside the spaceship, everything seems normal. Your heartbeat, your clock, the conversation you're having with a computer, all of it proceeds at a regular pace. You feel like time is passing normally, but your friend's perspective is drastically different. From their distant, gravitational, pull-free vantage point, they see your spaceship moving in slow motion. Your clock appears to be ticking slower. Your movements become sluggish, and your voice, if they could hear it, would be a deep, drawn-out groan. The closer you get to the event horizon, the more extreme this effect becomes. Time for you is slowing down relative to time for your friend. This isn't just an illusion, it's a real physical effect. According to general relativity, gravity is not a force in the traditional sense, but rather a curvature of spacetime. The more mass of an object, the more it warps this fabric, and a black hole is the ultimate example of this curvature. This warping affects not only the paths of objects, but also the flow of time itself. Clocks in a stronger gravitational field tick more slowly than clocks in a weaker one. We even have to account for this effect on Earth. The clocks on our GPS satellites run slightly faster than clocks on the ground because they are in a weaker gravitational field. Black holes simply take this effect to its most extreme and mind-boggling conclusion. As you approach the event horizon, the time dilation becomes infinite. To your friend watching from afar, you would appear to slow down so much that you would seem to freeze in time right at the edge of the black hole. The light you emit would become stretched to longer and redder wavelengths, a process called gravitational redshift, until it would eventually fade to a point where it could no longer be seen. To your distant friend, you would never actually cross the event horizon. You would appear to be a ghost forever suspended at the brink of the abyss. The predictions of general relativity were initially so strange that even Einstein himself was skeptical of some of the consequences. One of the first to apply Einstein's equations to the problem of a collapsed star was physicist Karl Schwarz. Just months after general relativity was published, Schwartz found a solution to the equations that described a non-rotating spherically symmetric black hole. His work predicted the existence of the event horizon, the boundary beyond which escape is impossible, and the Schwartz radius, which determines the size of this horizon based on the black hole's mass. Later physicists like Royo would extend this work to describe spinning black holes, which are far more common in the universe. Kerr's solution introduced a concept called the ergosphere, a region outside the event horizon where spacetime itself is dragged along by the black hole's rotation. Objects in this region can gain energy from the black hole spin, a phenomenon known as the Penrose process. General relativity also explains several other bizarre phenomena associated with black holes, such as gravitational lensing, where the black hole's gravity bends the path of light from a distant star, making it appear in a different location, and gravitational time dilation, where time slows down for objects in a strong gravitational field. These aren't just theoretical curiosities. They are effects that have been observed and measured, providing strong evidence for the validity of Einstein's theory and the existence of black holes die in a very real sense. General relativity is the language of black holes. It's the framework that allows us to understand their structure, their effects on the surrounding universe, and the extreme physics that governs their existence. Without Einstein's revolutionary insight, black holes would still be an unimaginable mystery, a figment of a sci-fi writer's imagination rather than a fundamental and proven part of our universe. Quantum mechanics versus black hole physics. Our exploration of black holes has so far been primarily guided by general relativity, Einstein's brilliant theory of gravity. It's a theory that works wonders on the grand scale, explaining the orbits of planets, the bending of starlight, and the very existence of black holes. But as we get closer to the heart of these cosmic monsters, we encounter a fundamental problem. The physics that describes the universe on the larger scales, general relativity, is in direct conflict with the physics that governs the smaller scales, quantum mechanics. This clash is one of the biggest challenges in all of modern science. Quantum mechanics is the strange and counterintuitive theory that describes the world of subatomic particles, the world of electrons, protons, and photons. It tells us that on this tiny scale, particles don't have a single location or a definite momentum. They exist in a cloud of probabilities. Quantum mechanics is incredibly successful, accurately predicting the behavior of lasers, transistors, and all the technology that powers our digital world. But it's a world built on principles of uncertainty and randomness, a stark contrast to the smooth, predictable, and deterministic universe described by general relativity. The conflict between these two pillars of modern physics becomes a critical issue at the singularity inside a black hole. General relativity predicts a point of infinite density and zero volume, a place where its equations break down. This is where quantum mechanics should, in theory, take over. The singularity is a place so small and so dense that both gravity and quantum effects should be equally important. We need a theory that can describe how gravity behaves on the quantum scale, a unified theory of quantum gravity. But such a theory does not yet exist. The two frameworks use different mathematical languages and make different assumptions about the nature of reality. General relativity sees spacetime as a smooth, continuous fabric like a sheet of silk. Quantum mechanics, on the other hand, suggests that spacetime, like all matter and energy, might be quantized or made up of discrete tiny chunks, like a digital image made of pixels. Trying to force these two perspectives together leads to nonsensical results like infinities popping up in our equations. This conflict is most famously embodied in the information paradox. According to quantum mechanics, information about a particle state can never be truly destroyed. If you burn a book, the information in it is not lost. It's just scattered in the smoke and ash, and in principle could be retrieved. However, general relativity and our simple understanding of black holes suggests that when something falls into a black hole, all information about it, its chemical composition, its history, its quantum state is lost forever, compressed into the singularity. This is a direct violation of a fundamental principle of quantum mechanics. The ER equals EPR conjecture links black holes and quantum entanglement. This suggests entangled particles might be connected by tiny wormholes. Black holes could be fuzzballs in string theory. Instead of a singularity, they are dense balls of strings without an event horizon. Time inside black holes may behave differently than we imagine. Some theories propose nonlinear or looping time within the singularity region. Some scientists hypothesize black holes are gateways to time travel. Though highly speculative, rotating black holes might permit closed time-like curves. Black holes might store information on a 2D surface like a hologram. The holographic principle radically changes our understanding of space and information. They could be the key to uniting quantum mechanics and gravity. Studying black holes is central to developing a theory of quantum gravity. This idea envisions the Big Bang as a kind of black hole explosion. Black holes challenge the very notion of reality and causality. Their extreme physics pushes the limits of what we know about time, space, and existence itself. Black holes can strip gas from nearby stars. Their gravity pulls matter off the star's surface, feeding the black hole's accretion disk. Some stars orbit black holes for millions of years without falling in. If their orbit keeps them far enough away, they can remain stable despite the black hole's pull. Binary black hole systems eventually merge. Over time, they lose energy through gravitational waves until they spiral together. Stellar clusters can harbor intermediate black holes. The dense environment can help funnel stars and gas into the center, feeding the black hole. Passing too close to a black hole can eject a star from a galaxy. Tidal disruption events occur when stars get torn apart. As it spirals into the black hole, visible across great distances, debris from disrupted stars can fuel the black hole. Part of the star's material falls inward, increasing the black hole's mass. This happens when the black hole intermittently consumes material from its companion star. Planets could theoretically orbit black holes. If they're far enough away, stable orbits are possible even without a nearby star. Such planets might still be habitable if heated by other sources. They could get warmth from tidal heating, geothermal activity, or light from a nearby accretion disk. The gravity near a black hole is millions to billions of times stronger than Earth's. Temperatures in accretion disks can reach millions of degrees. Friction, compression, and magnetic turbulence heat the gas to extreme levels, causing it to emit X-rays. Particle jets move at relativistic speeds. These jets are blasted out along the poles of the black hole, traveling at nearly the speed of light. Magnetic fields near black holes can be extremely intense. The environment around a feeding black hole is saturated with dangerous gamma rays and X-rays. The innermost stable circular orbit is closer for rotating black holes. Spin drag spacetime with it, allowing matter to orbit closer before falling in. Falling into a black hole would be fatal long before reaching the singularity. Radiation, tidal forces, and the heating of surrounding material would destroy you first. Supermassive black holes have weaker tidal forces at the horizon than smaller ones. You could theoretically cross the event horizon without being torn apart immediately. Falling into a supermassive black hole might be painless at first. Only after approaching the singularity would tidal forces become deadly. The center of galaxies can be violently energetic due to black holes when actively feeding these regions. Called active galactic nuclei, can outshine the rest of the galaxy. Schwartz radius is the radius of the event horizon for non-rotating black holes. This radius grows linearly with mass. A black hole twice as massive as another will have twice the Schwartz radius. The Kerr metric describes rotating black holes. It's a solution to Einstein's equations that accounts for angular momentum. The Einstein field equations predict black hole formation. These equations describe how matter and energy curve spacetime. Geodesics describe how matter and light move in curved spacetime. Near a black hole, geodesics curve steeply toward the event horizon. Light cones tilt inward near the horizon. This means that all possible paths lead toward the singularity. Null geodesics show paths of light near black holes. They reveal how light bends and spirals before crossing the event horizon. Penrose diagrams map spacetime around black holes. These diagrams show causal relationships and how different regions connect. Metrics change for charged versus uncharged black holes. Black holes slowly evaporate via Hawking radiation. This quantum process causes them to lose mass over extremely long time scales. Stellar mass black holes take far longer than the age of the universe to evaporate. They would need trillions upon trillions of years to completely vanish. Small black holes evaporate faster. Primordial black holes could be evaporating today. If they formed just after the Big Bang and were small enough, they might be disappearing now in bursts of energy. The last objects in the universe may be black holes. After stars die and galaxies fade, only black holes will remain for unimaginable spans of time. Eventually, even supermassive black holes will evaporate. This is predicted to happen in the distant black hole era of the universe, following Einstein's E equals mc2e equals mc caret 2e equals mc2. The final stage of evaporation would be extremely energetic. The black hole would release a massive burst of gamma rays and particles in its last moments. In the far future, the universe could be dark and nearly empty. After black holes vanish, only very low energy radiation would remain. This idea is speculative, but ties into certain cosmological models. Black holes can sing in gravitational waves. When they merge, the vibrations of spacetime ring like a bell. This is called the ring gown phase. Black holes have no hair. This physics phrase means they can be fully described by just three properties: mass, spin, and charge. They erase all details of what falls in, except for those three traits. From the outside, there's no way to tell what the black hole has consumed. You could orbit a black hole indefinitely at the right distance. Just like planets orbit stars, stable orbits are possible far enough from the horizon. The brightest quasars are powered by such disks, fed by supermassive black holes. Black holes can be part of triple systems. Time travel to the future is possible near black holes. Due to gravitational time dilation, an observer could experience much less time passing compared to faraway regions. The Milky Way likely has millions of stellar black holes. Most are undetected because they're isolated and not actively feeding. Black holes could help detect extra dimensions. If extra dimensions exist, they might subtly alter black hole evaporation rates or gravitational wave patterns. The term black hole was popularized by physicist John Wheeler in 1967. Before that, scientists are trying to image Sagittarius A** better than ever. New data from the Event Horizon Telescope aims to sharpen the image of our galaxy's central black hole. Quantum computing may help solve black hole puzzles. Simulating black holes on quantum computers could reveal new physics about their interiors. LIGO and Virgo continue to detect black hole merges regularly. These observations help us understand black hole populations and their formation. There's ongoing research on black hole echoes. These hypothetical signals could indicate new physics. Near the event horizon, some researchers study black hole firewalls. Theories about gravstars challenge black hole models. With neutron stars cause these mysterious signals. Black hole merges teach us about the universe's expansion. Gravitational waves can be standard sirens to measure cosmic distances. Scientists are exploring quantum hair on black holes. This idea could solve the information paradox by adding subtle quantum details to the horizon. New telescopes will probe black holes at higher resolution and across wavelengths. Instruments like the James Webb Space Telescope complement EHT by observing accretion and jets.